So, we have done in the previous class that average velocity that came out to be n by 3n plus 1 into delta p by 2 k L to the power 1 by n r to the power n plus 1 by n, right. This we saw. Also we saw V max, right. V max was equal to, just a minute, V max was equal to n by n plus 1 into delta p by 2 k L to the power 1 by n and r to the power n plus 1 by n, right. This is true for any fluid following the power law equation, right. And we said for V max that if we add in limiting condition for V max, we saw that when n becomes equals to 1 and k becomes equals to mu, then under limiting condition this has become the same expression as we obtained for Newtonian fluid flowing through a conduit or pipe, right, having radius r. This we had established. Now, let us also look into that limiting situation. So, under limiting condition, when n becomes equals to 1 and k becomes equals to mu, the average velocity is 1 by 3 plus 1, right, divided by delta p by 2 mu L to the power 1 by n is 1, r to the power n plus 1, that is 1 plus 1, 2 by 1 r square, right. So, this we can write is delta p by 2 into 3 plus 1, 4, 8 mu L r square, right. If you see, this is the same as that of the Newtonian fluid. So, this is true for Newtonian fluid, right. So, that means the thing which we have developed, which we have derived is correct, because it is also having the same value when we are putting limiting condition, right. So, let us look into that our slide also, because this you will get, you can see online that V average is 1 by 2 pi r square 0 to r V into 2 pi r. We have done all in detail, we take every steps, but here we might have omitted some. So, V into 2 pi r into dr. So, that becomes 2 by r square 0 to r V r dr. Substituting the value of V, it becomes 2 by r square n by n plus 1 delta p by 2 k L to the power 1 by n, the integration between 0 to r to the power 1 by n plus 1 minus r to the power 1 by n plus 1 times r dr. So, this becomes 2 by r square into n by n plus 1 into delta p by 2 k L to the power 1 by n times capital R to the power 1 by n plus 1 times r square by 2 minus capital R to the power 1 by n plus 1 times r square by 1 by n plus 3, right. So, this on simplification becomes n by n plus 1 into delta p by 2 k L to the power 1 by n into 1 minus 2n by 3n plus 1 into r to the power 1 by n plus 1. So, that becomes n by 3n plus 1 into delta p by 2 k L whole to the power 1 by n, right, whole to the power 1 by n into r to the power n plus n by n, right. So, this is the average velocity, right, and we also have seen V is V max, that was 1 minus R by R to the power n plus 1. V was V max, that is this V max was n by n plus 1 delta P L by L K L, right, and V we had shown that V was, one second, V was, yes, V was this, right, V was this n by 3 n plus n plus 1 delta P by 2 K or R to the power n plus 1 by n into 1 minus R by R to the power n plus 1, right. If this is true, then we can write that V is equals to, and V max we have shown that V max was, this is the average or this is the instantaneous velocity, this was V is V max, right. So, this is V max. So, we can now write that V is equals to V max, we can now write V is equals to V max into 1 minus R by R to the power n plus 1 by n, right, and also we can write V average is equals to V n plus 1 by 3 n plus 1 to the into V max, right. This we can write for any power law fluid, right. So, for power law fluid we saw V is V max into 1 minus R by R to the power n plus 1 and V average is n plus 1 by 3 n plus 1 into V max, right. Now, as we said that under limiting condition, here also we put if n is equals to 1 and k is equals to mu, right, that is that Newtonian fluid, it becomes Newtonian fluid from non Newtonian, n is equals to 1 and k is equals to mu. We can then write V is equals to n by n plus 1 into delta P by this we have also shown 2 K L to the power 1 by n into R to the power n plus 1 by n minus small r to the power n plus 1 by n, right. So, it becomes the same for Newtonian fluid for, of course, this is for non Newtonian, otherwise you will be misled. So, this is for non Newtonian. So, this becomes, if we put n is equals to 1 and k is equals to mu in this, then n is equals to 1, that is 1 by 2, this is delta P by 2 mu L, this to the power 1 and this is R to the power n is 1 1 plus 1 by n, that is 2 R square minus R to the power n plus 1 by n R square, right. So, that means this is delta P by 4 mu L into R square minus R square, that is equals to delta P by 4 mu L into R square into 1 minus R by R whole square. So, for Newtonian fluid which we had developed, right. So, this is V, and similarly we can also say that V max is equals to n by n plus 1 into delta P by 2 KL to the power 1 by n into r to the power n plus 1 by n. This was for Vmax when, and this is for non-Newtonian fluid. And when we are writing n is equals to 1 and k is equals to mu, then V max becomes equals to, this is 1 by 2, this is delta p by 2 k mu L, right, to the power 1, and this is r to the power square, right. So, V max is then equals to delta p by 4 mu L r square, right, and this is for Newtonian fluid. Under limiting condition, right, and the average velocity V average, we have seen it is n by 3 n plus 1 into delta p by 2 k L whole to the power 1 by n, r to the power 1 by n or n plus 1 by n, right. This is for non-Newtonian fluid. Now, if we put the limiting condition n is equals to 1 and k is equals to mu, then we can write average V average is, this is 1 by 4, right, into delta p by 2 mu L, this is 1, r to the power 1 plus 1 by n, so r square. So, that means this is delta p r square by 4 8 mu L, right. So, this is for Newtonian fluid. For all Newtonian fluids, for all these expressions we had developed earlier. If you do a backtrack, you can definitely get it that we have done these things for the Newtonian fluids, right. So, that means the expressions are correct. Under limiting conditions, they are showing that what is the value for the Newtonian fluid when limiting condition is n is 1 and k becomes mu for the expression developed for all the fluids, that is non-Newtonian fluids, right. So, when non-Newtonian fluid becomes Newtonian, then the expressions which we developed earlier for instantaneous velocity, for maximum velocity and for the average velocity, the expressions are identical, right. This concludes that the derivations which we have done are true, right. So, this you try. Now, we say that the average velocity equation we can write that V average is equals to n by 3 n plus 1, right, into delta p by 2 k L to the power 1 by n r to the power n plus 1 by n, right. So, this we can rewrite delta p by 2 k L, this to the power 1 by n, right. This is equal to 3 n plus 1 by n into V average by r to the power n plus 1 by n, right. This also we can rewrite as delta p by delta p r, okay, by 2 k L to the power 1 by n is equals to 3 n plus 1 by n, right, into this means this term we can rewrite as V average right, divided by r into r to the power 1 by n, right. This we can rewrite as r into r to the power 1 by n. So, when we have taken out this 1 by n here, so remaining is 3n plus 1 by n V average by r, right. So, that becomes this. So, this we can rewrite, or delta p r is say r by 2, or it becomes 2 if we write in terms of d, that is r by 2, that is 4 k L whole to the power 1 by n. This is equals to 3 n plus 1 by n, and if we convert it r by 2 is d, that is 2 V average divided by d, right. This is true. Now, this we can rewrite as delta p d by 4 k L. This is equals to 3 n plus 1 by n. This 1 by n, okay, this 1 by, okay, let us write again, otherwise it is out of that thing. This was 2 V average over d, right. So, if you write delta p d by 4 k L, this is equals to 3 n plus 1 by n whole to the power n, because this when goes there is inversed. So, to the power n, and this also becomes equals to 2 V average by d to the power n, right. So, we can write delta p d by 4 k L, right. This is equals to delta p d by 4 L. So, if we take k out, k is here into 3 n plus 1 by n to the power n into this. If we write like this, okay, if we write like this 4 n, right, we can write 3 n plus by 4 n. So, here we can write 8 V average divided by d to the power n, because this 4 to the power n we have put in the denominator. So, we have put here in the numerator. So, 2 into 4, 8 V average by d, right. So, this we can rewrite that delta p d by 4 L, this is equals to a new constant k prime into 8 V average by d to the power n prime, right, where k prime is equals to k into 3 n plus 1 divided by 4 n, and n prime is equals to n, right. So, if this is true, then we can write delta p d by 4 L, this is equals to like that, okay. K prime, new constant k prime is k into 3 n plus 1 by 4 n, and n is equals to n prime, right. Now, in this equation, that is delta p d by 4 L is equals to k prime 8 V average d prime, right. So, say this is equation A, right. So, now in equation A, So, it was delta P d by 4L. This is equals to K prime 8 V average by d to the power n prime, right. So, if this equation we rewrite that this is nothing but tau w, right, because this tau at the wall is delta P d by 4L, right. Tau w, that is tau at the wall, is delta P d by 4L, right. So, tau w that becomes equals to K prime into that okay, if we say that this into minus dV dr to the power n prime at the wall, right, dV dr at the wall. This we have shown earlier, right. This we have shown earlier also in earlier expression. If you go back, trace back, that tau w, that is shear stress at the wall, is delta P d by 4L, and that is equals to K prime, and dV dr with negative at the wall, that becomes equals to 8 V average by d, right. So, we can write where V average is equals to d by 8 delta P d by 4 K prime L whole to the power n prime, right. So, V average we can rewrite d by 8 delta P capital D by 4 K prime L, right. So, this is called generalized coefficient of viscosity, generalized coefficient of viscosity, right. And this now viscosity means shear stress by shear rate, right. So, shear stress by shear rate is the viscosity. So, this is equals to the slope of the straight line for Newtonian liquids. So, if we had a plot, this is shear rate and this is shear stress. So, this was the Newtonian fluid, and that is the slope of the line is this, right. Slope of the line is that. Slope of the straight line for Newtonian fluids, right. For non-Newtonian fluids, we can say that shear stress over shear rate, this relationship varies with shear rate, right. This relationship varies with shear rate, and the slope is called apparent viscosity, or this can be termed as mu prime, right, which decreases with increase in shear rate for pseudoplastic fluids and increases with shear rate for dilatant fluids, right. So, if you remember, it was like this for pseudoplastic, and for dilatant it was like this, right. So, if we say that for dilatant fluid, with the increase in shear rate, the increase in the shear the fluids increases the shear rate, but the shear stress is to shear rate. This relationship varies with shear rate, and the slope is called apparent viscosity, which decreases, that is apparent viscosity decreases with increase in shear rate for pseudoplastic fluids and increases with shear rate for dilatant fluid, right. So, this is true. So, till now this we have done, and apparent viscosity we have shown, and next time we will also talk about the apparent viscosity and the Reynolds number of the non Newtonian fluids, right. Thank you.